Limit laws, part 1. Here are some limit laws. They might look a little bit complicated, but try not to worry too much. You want to be able to understand these formulas and apply them, but you don't necessarily have to memorize exactly what these look like and be able to recite them. The first thing to keep in mind is that c is a constant, and the limits, so the limit as x approaches a of f of x, and the limit as x approaches a of g of x, both need to exist. So that means that neither of these limits can evaluate to d and e, or does not exist. So they are not d and e. Another thing to keep in mind is c is a constant, or usually in Calc 1, a constant is going to be a number. N is also a constant in this case. So let's take a look at what some of these limit laws actually mean. So if we take a look at these 3 limit laws here, what they're telling us is that we can do things in different orders. So we can either add 2 functions together and then evaluate our limit, or we can evaluate the limit of each function and then add, or subtract of course, the 2 limits together. We can multiply 2 functions and then evaluate the limit of that product. Or we can find the limit of each of the functions and then take the product of those limits. We can divide 2 functions and then evaluate the limit of that quotient. Or we can evaluate the limits first and then divide the limits. Deciding which way you want to do it is going to depend on which way is the easier way to do it, and being able to determine the easiest path just comes from more experience and looking at some examples. Similar to these, you can multiply a constant times a function and then evaluate the limit, or you can evaluate the limit then multiply by a constant. You can raise a function to a power and then evaluate the limit, or take the limit of the function and then raise that limit to a power. And then this last one is a little more similar to those other ones than the ones in the middle. So you can take the natural log of a function and evaluate the limit, or you can evaluate the limit and then take the natural log. Then 2 more. The limit of a constant is a constant, so like the limit of as x approaches anything of 5 is 5. I should probably write that. The limit as x approaches any number of 5 is equal to 5. And if you have the limit as x approaches a of x raised to the nth power, that's going to be equal to a to the n. In addition to the limit laws, another super useful property for evaluating limits is the direct substitution property. And this is if f being a function, the thing that we're taking the limit of, is a polynomial or a rational function, and a is in the domain of f, which is very important. Then the limit as x approaches a of f of x is f of a. So that means we can directly substitute this a in for x, and that will evaluate our limit. Notice that that limit is gone after we've directly substituted. So it's just an f of a, we don't have an lim anymore. So let's take a look at 2 examples of this. So we have the limit as x approaches 1 of x squared plus 2 over x plus 3. So using the direct substitution property, we can directly substitute 1 in for each of our x's. So we have 1 squared plus 2 over 1 plus 3. 1 squared is 1, so I have 1 plus 2 over 1 plus 3, which is equal to 3/4. So the limit as x approaches 1 of x squared plus 2 over x plus 3 is 3/4. Now let's take a look at this next limit. So we have the limit as x approaches 1 of x squared plus 2 over x minus 1. And if we try to directly substitute, we will get 1 squared plus 2 over 1 minus 1. Now it'll be equal to 1 plus 2 over 0, and that means that this is undefined. So something weird happened here. Well, if we look at this, first one, example 1a, the limit as x approaches 1 of x squared plus 2 over the quantity x plus 3, 1 is in the domain of that x squared plus 2 over x plus 3. Whereas if we look at example b, 1 is not in the domain of x squared plus 2 over the quantity x minus 1. So we cannot actually use the direct substitution property to help us evaluate this limit. We'll have to figure out some other method for evaluating that limit. Before we look at what to do when you can't use direct substitution, let's take a look at a couple of examples of limit laws and combining limit laws with direct substitution. So for example 2, we have the graphs of two functions, the graph of f of x and the graph of g of x. And we want to find the limit as x approaches 2 of the quantity f of x plus g of x. So as this is written, we need to first add f of x and g together, and then afterwards evaluate the limit. But adding two graphs of functions together is not something that is going to be very efficient. So instead, let's apply one of our limit laws. So we'll rewrite this as the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. So first we'll evaluate the limit of each function, and then we'll add those limits together. So let's start by finding the limit as x approaches 2 of f of x. So we need to take a look at this graph and take sort of an informal left and right limit to help us out with this. So as we look at the limit as x approaches 2 from the right, it seems that as x gets closer and closer to 2, f of x is getting closer and closer to 2 as well. And if we look at our left limit, the left-hand limit as x approaches 2 of f of x is also 2. So the overall limit as x approaches 2 of f of x is 2. And we'll add that to the limit as x approaches 2 of g of x. So now we need to look at the left and right limit for this. And let me label that 2. So 2 is over there. So for my right limit as x approaches 2, it seems like f of x is approaching 0. And for my left-hand limit as x approaches 2, f of x is approaching 0. So my left and right hand limits are equal, so the limit as x approaches 2 of g of x is 0. And now I can just add this together. So 2 plus 0 is 2. Sorry that my 2 formatting keeps changing. I just can't decide whether I like 2 or 2. Okay, so the limit as x approaches 2 of the quantity f of x plus g of x is 2. For this example, we have the same graphs of f of x and g of x, but we have a different limit to evaluate. So we want to find the limit as x approaches -1 of the quantity f of x minus g of x. So right now it's asking us to first subtract the functions, and then evaluate the limit. But just like it doesn't make sense to add the graphs of two functions, at least in an efficiency point of view, it doesn't make sense to subtract the graphs of two functions if we're trying to be efficient here. So let's instead take the limit of each function before subtracting them. So we'll apply that limit law when we have the limit as x approaches -1 of f of x minus the limit as x approaches -1 of g of x. And notice that I'm writing this x approaches -1 each time. You want to be sure that you're writing all of the parts of that limit, because if we have the limit as x approaches 5 for something, that's not going to be the same thing as the limit as x approaches 4 for every single function. So they're not actually equivalent. And it doesn't make sense to just write limit, because then we don't know what we're trying to approach. That's not enough information. So make sure you're writing that x approaches whatever it's approaching each time. Okay, now that we've used our limit law to rewrite this, we can evaluate each of these limits. So let's start by finding the limit as x approaches -1 of f of x. Okay, so -1 is right over here. We'll take a look at our right and left hand limits. So approaching from the right, as x approaches -1, it appears that f of x is approaching -1. I can draw this in if it makes my axes a little more clear. And then taking a look at our left-hand limit, as x approaches -1, f of x is also approaching -1. So the limit as x approaches -1 of f of x is -1, since our left and right hand limits are equivalent. And then we need to subtract the limit as x approaches -1 of g of x. Okay, so let me sketch in those axes a little bit darker. -1 is over here for x. So taking my right hand limit, as x approaches -1, f of x is approaching 0. And for my left hand limit, as x approaches -1, g of x, I might have said f of x by accident, but g of x is approaching 0. Now that we've evaluated our limits, we can find the difference between them. -1 minus 0 is -1. So the limit as x approaches -1 of the quantity f of x minus g of x is -1. Again, same functions for f of x and g of x, but now we have a different limit. We want to evaluate the limit as x approaches 0 of the quantity f of x times g of x. So let's use our limit laws to rewrite this as an easier product, where first we'll find the limit of each function. So we have the limit as x approaches 0 of f of x times the limit as x approaches 0 of g of x. And now that we've rewritten this with our limit laws, we can evaluate our limits. So we need to find the limit as x approaches 0 of f of x. So we'll take our right and left hand limits, and we find that as x approaches 0 for f of x is approaching 0. And then we need to find the limit as x approaches 0 of g of x. So tracing from our right hand limit, it's about 1.3-ish. It's less than 1.5, so we'll go with 1.3-ish. And the left and right hand limits are both approaching about 1.3. So we have 0 times 1.3, and 0 times 1.3 is just 0. So the limit as x approaches 0 of the quantity f of x times g of x is 0. Now let's take a look at the limit as x approaches 1 of f of x divided by g of x. Let's split this up using our limit laws. So we have the limit as x approaches 1 of f of x all over the limit as x approaches 1 of g of x. So now we can evaluate the limit of each function before dividing them. Let's take a look. The limit as x approaches 1 of f of x, if we take our right and left hand limits as x is approaching 1, f of x is coincidentally also approaching 1. And then we need to take the limit as x approaches 1 of g of x. So looking at our right hand limit, it appears that as x approaches 1, f of x approaches 1. And for our left hand limit, as x approaches 1, g of x approaches 2. Oh no! Our left and right hand limits are not equal. So this overall limit does not exist. Which means that we're not able to just use limit laws to evaluate this. So we will say that this does not exist. Let's look at one more example with these graphs. This one looks a little bit different because we have the limit as x approaches 2 of the quantity x cubed times f of x. So we can think of this x cubed, and we don't even have to think of it, it just is another function. So we have this function x cubed times this function f of x. So we can use our limit laws here. So this is equal to the limit as x approaches 2 of x cubed times the limit as x approaches 2 of f of x. Because trying to multiply this graphical representation of f of x times this algebraic representation of x cubed, not going to work out well. But since we've applied our limit laws, we can now evaluate this. Looking at the limit as x approaches 2 of x cubed, we can either use our one limit law, where we have the limit as x approaches a of x to the n is equal to a to the n. That's one way to look at this. Or you can just use direct substitution, where since x cubed is a polynomial, we can directly substitute 2 into x. Either way you want to think about this particular problem is okay. Personally, I just always use direct substitution. It's the same, it'll look exactly the same, but my brain goes direct substitution because fewer things to think about. So let's directly substitute 2 in for x. And let me use a different color because this is not g of x, so 2 in for x. So that's either using direct substitution or this limit law up here. The step will look identical. And we're going to multiply that 2 cubed by the limit as x approaches 2 of f of x, which we've actually already found before, and we found that that was 2. So we have 2 cubed times 2. You can either think of this as 2 to the 4th, or you can think of it as 2 cubed is 8. And then 8 times 2 is 16. So the limit as x approaches 2 of the quantity x cubed times f of x is equal to 16.